at me? Because you are not allowed to play YouTube videos inside your YouTube video, I learned. So yes. So you heard the analogy of a black box, right? What's hilarious to me about Mplus is that it's literally a black box that pops up on your screen when you run it. It's a little DOS window that shows that it's running. Remember what DOS is? I'm dating myself again. It's a little DOS window, and it pops up, and it's black, and then answers just spit out magically. But I want you to know just a tiny bit about the process by which it's finding answers, because that is how model fit gets created. And it's one of those things that people do not understand, I think, as well as they should. And then they say bonehead things in dissertation defenses like, well, what if you turn the arrows around? Would the model fit better? And I'm like, no, that's not how it works. So I don't want any of you to say bonehead things during anyone's dissertation defense, including your own. So yes, what are we trying to make taller? We're trying to make data taller as a function of item parameters. So we already know what these are. So let's say that we're trying to estimate the picture that I keep showing, 3 items, 2 factors. That's our picture. So what are we trying to find simultaneously? Measurement model. If we have 6 items, we have 6 intercepts. If we have 6 items, we have 6 residual variances. If we have 6 items, we have 6 factor loadings. In that picture, we have 2 factors. If each one needs a scale, so let's say mean 0, variance 1, then the only structural model parameter we're talking about then is the covariance between them. So in total, we have to find 19 things simultaneously. That's what the algorithm is doing for you, trying to find 19 answers. The items are what's known as fixed effects. What you get back per item is one number that characterizes that item's intercept, another number that characterizes that item's residual variance, and one more number that characterizes its loading. So the items are not exchangeable. Each one gets its own set of answers. In contrast, the people are exchangeable. The people are random effects. Even though there's an F in the equation where each person gets their own factor, at no point in this process are those F's solved for. They're irrelevant. The idea is that all we need to know, given that the F's are supposed to be multivariate normal, and given that the items are supposed to be characterized by a multivariate normal distribution, the factor means, variances, and covariances are what's known as sufficient statistics for the F's. The F's are not real. They're factor scores. They're latent. They're pretend. They are the same thing as random intercepts and slopes in the world of multi-level. And just as in that world we can predict random intercept variance and we can predict random slope variance, we can predict factor score variance without ever figuring out what the F is for each person. We don't need it. So people are random. We're not going to get F's as part of this process unless we ask for them. But they are after-the-fact predictions. They are not things being found simultaneously. So the only factor thing that is being found in this instance is the covariance between the two, because we've already told it mean 0, variance 1 for each of the 2 factors. So maximum likelihood is the way that these models are estimated. It wants to be taller. It's all about taller. So there's 3 steps here. It has to figure out the best answer. It has to figure out if that answer is really good or just the best of a series of crappy alternatives. And then it has to describe how well our set of answers actually mimic the original data. So how does all this happen? Let's start with univariate normal and think about that in univariate space because that's easier than multivariate. Taller. So the normal distribution actually is one of the scarier formulas in statistics. Here it is. You're familiar with the shape though, right? I stole this from Wikipedia. Normal distribution has 2 parameters that describe it, a mean and a variance. The y-axis of this picture is a measure of height, quite literally. It's likelihood. You can think of it as something like probability, but probability is technically only applicable to distributions for categorical data. For continuous data, it's known as likelihood, but it's easier if you hang on to height. So if I am, let's say that I have a 2. All right, I'm this yellow person right here. Let me get a screen pointer. There's your pointer. Here I am. This is me. I'm sitting right here. I'm me. I have a 2 on my outcome. That's what I know about me. The question is, in combination of with me and everyone else, what is the most likely estimate for the mean and the variance that makes the sum of the data as tall as possible? So for me, the most likely one would be a 2 with some variance around it, but that doesn't describe everybody. We have to come up with a distribution that describes everybody simultaneously. So it's this process of saying, well, if the mean were 0 and the variance were 2, fill in the formula. So if we go down here, here's my formula for height. So here's a square root. There's a 2. What's that thing? Pi. What's pi? Yeah. Exactly. Oh, boon, as my son would say. That's very impressive. So yeah, it's a number, though, right? It's a number. Sigma squared, that's a variance. E to the, that's another number. Here's another number. Here's variance again. And then here's me minus the mean. So there's another number. So if I plug in mean 0, variance 2, I get a height for me. People are supposed to be independent, and so if you take 2 heights, you can get the combined height of the 2 heights if they're independent by multiplying them together. But that number gets really small really fast, so someone smarter than me figured out, hey, you know what? If you take the log of that height, then you can add people's heights together. Because if you do a log, what used to be multiplied is added, and what used to be divided is subtracted. So it makes the math a lot easier. So I get my height, and then I get yours and yours and yours and yours and yours and yours and yours, and I add them all together, and I get a number. And then we try out another combination, and I'd get my height and yours and yours and yours and yours, and we add them all together. And then it's like, well, is that new guess taller? If so, we're heading in the right direction. If it's not taller, we chuck it and we move on to something else. So this process of trying to make everybody as tall as possible at the same time, that's what it's going for. And this is in univariate space, but the same thing plays out in multivariate space as such. Now, I will reiterate to you, at no point will you be doing any matrix anything, okay? I just want you to see this because it's important in thinking about what your model is doing and why fit stops mattering halfway through this course. So here's the univariate equation, rearranged a little bit for comparability with multivariate. But just as we had a mean and a variance in univariate data, for multivariate, like for my 6 items, we swap out a single residual variance for this thing right here. What is that thing? Sigma. Do you remember what that was? It's the sum, but in this case, sigma means something very specific. And I don't expect you to remember this off the top of your head, but I will show this to you because we did talk about it at one point. Sigma is the predicted variance covariance matrix across your items. To get to this, you need to know your loadings, your factor variances, and your factor covariance, as well as your error variances per item. So sigma is what the data are supposed to look like if your model is right. It's the predicted matrix. And this same slide, the next one here, shows how each spot in this ginormous matrix gets filled in. The predicted variances are its loading squared per item times the variance of the factor plus error. So true score plus error score for each of those. The off diagonals, the predicted covariance, is a function of the loading of the two items it's the covariance for, times the factor variance if they're on the same item, or times the factor covariance if they're on different items. So those 6 loadings, the factor covariance, that's enough to make that whole thing. Back to this. So we've replaced this idea of residual variance for a single item with a covariance matrix for all of them. The bar around it is a term called the determinant. Roughly speaking, it summarizes how much non-redundant info is in the matrix, and that number then is essentially divided. It takes the matrix inverse in the formula. So you will see an error message sometimes that says a matrix is not positive definite. That means that that part of the formula broke when it tried to make your model, and your model is broken and you can't keep it. So non-positive definite is bad. It means that this part doesn't work. Sigma then shows up again in here, as well as the mean vector that characterizes all of your items. So point of the story, though, this thing, once you know a guess for all your loadings, your factor covariances, and your item means for each person, you get f of y, which is a number. So picture this, like if you think of the univariate as like, this shape, and bivariate would be like a taco. I can't draw any further dimensions than that, but if you just like picture like a big pile of multidimensional stuff, right, taller, each person gets one number that summarizes their height in multidimensional space. If people are independent, we take the log of that number, we add it up, and the sum total of that is the log likelihood for the sample. We then go through and fill in different guesses for what the loadings would be, what the factor covariance would be. Each person gets a height. Sum the log of the heights again. Is that total taller? Yay, you win. We're heading in the right direction. If it's shorter, nope, go back to what you started from. So the process of going through and figuring out which numbers you should try next, that's all calculus. I don't need you to know that with any level of specificity. The idea is that it keeps trying things as it tracks its improvement in height to the point where it doesn't really change very much and it decides it's done. So there are convergence criteria that it uses to decide when it's done. For instance, 0.00005. If it keeps trying new answers and the sum total of the height for the sample doesn't get any better by that, it declares itself done. So each person's set of item responses gives them a height based on the predicted covariance matrix for the sample. We sum all of those heights together and we get one giant height. And that giant height in Mplus has a special name. It's given as the model HO log likelihood. Let me skip this for a second here. So just to give you a preview of what your model will look like, slide 45 here is some example Mplus output. You will see model fit information, log likelihood, HO value, right there. That's the height of your model. And the next one will be H1. H1 is going to be the height of the data, the best possible model when it lets everything be what it wants. So we end up with whatever estimates made everybody's mountains combined the tallest they could possibly be, and then how steep the grade is of the mountain contributes essentially to the standard errors for those. where the opposite of steep is standard error. So if you want something that's flat, that's a big standard error. Something that's very steep is a small standard error, very precise. And then you end up with all this stuff. So if you read textbooks on SEM, this is the kind of stuff that you're going to see. Let me break it down for you, though. So we have sigma. Sigma is predicted, right? It's what the pattern of covariance should be according to your loadings and your factor covariances, versus S, which is the right answer, the covariances that exist in the data. That's known as the saturated model in this context. It's also known as the unstructured model in multi-level context. It's known as H1. So you end up comparing your model, HO, to the best possible, let all the covariances just be whatever they want, H1 model, and you see how far off you are. So the difference between the two becomes a chi-square type statistic. And when you write it in terms of the matrix summary, it looks like this, and you'll see this in textbooks here, but this is basically the same thing. So there are two pieces of information that you have to memorize here, HO and H1. And I will be honest with you, it took me several years to not mess these up, but then someone asked me a question that made it impossible for me to ever forget again. So in her honor, as my closing thought to you, I want to tell you about this. So as you know, I have office hours in computer lab here. I did it back at UNL as well. And when I was teaching 2 classes at a time, the lab was usually full. It had up to 24 computers, and people had a queue waiting to talk to me. And so I'm helping someone do something, and all of a sudden, one girl hollers out to me, "Hey, Lisa, am I the hoe?" Like, what? Like, well, Lindsay, I really don't think it's my place to comment on your personal life, but what? Am I the hoe? Like, she's looking at Mplus output, and she's asking if she is the HO model or the H1. And so I wrote back, I'm like, yes, Lindsay, you are the hoe. Thanks. So I hate to tell you, folks, you are the hoe forever and ever. H1 is the right answer. It's the data. So the object is to get your hoe model as close to the H1 model as humanly possible. You are the hoe. So the H1 model will never change. It's a function of just the data. The HO model is the one that you told it to fit, and therefore it will change as a function of what you told it. So we're talking about potentially 3 different heights here, 2 of which we've been introduced to, drawing 3 rectangles on the board. One is H1. This is as tall as your data can possibly be. It's the best. It's not a model. It's literally just saying, what if we just let all the covariances be whatever they felt like and estimated them? How well would that do? It would be perfect. It's the answer key. It's as good as it gets. And then there's something that we haven't talked about yet called the null model, which is basically the crappiest possible model you would ever entertain. It's the simplest one that would be appropriate in a CFA context. And then there's yours, the hoe, the HO model. And your objective is to get as close to this H1 model as possible. So this is an example of a nested model comparison in which every time you are going for not worse. The H1 model has as many parameters as there are units of data going in. The HO model has fewer parameters to the extent that you have fewer loadings than you have covariances. And the difference between the two you are hoping is non-significant. You want them close. So all of the significance tests that you see on your output, such as this chi-square that you will get here, is a test of whether or not you are worse than the best model. And that's fit. How far off is your predicted covariance matrix from the one that's in the data, where yours is HO and the data is H1? And that's what these formulas are giving you, is a measure of offness. So to the extent that you get it right, HO is just as tall as H1. Okay. How are we doing? So yes, parting words, you are always the hoe. You'll never forget that again, I promise. Yes, thank you, Lindsay. She has the done kind too. So, all right. I will see you all Wednesday, and we'll look at the model fit in Mplus.